Good morning, everybody. I welcome you to today's webinar about BQR's solution. My name is Simon Zubler. I'm responsible for the FlowCAD Swiss office, and I want to give you just a short introduction about FlowCAD. So FlowCAD is your EDA partner, electronic design automation. We are offering tools for electronics development. And maybe you know this function here. I can also show you the graph of it. And here is where it comes from. So this is nothing else than the Moore's law. Moore's law is saying that the complexity of electronic circuits is doubling every second year. So that's the reason why you need tools for helping you in your daily work developing electronic circuits, but because it's no more possible to do all the different works manually by hand. So that's the reason we have a huge solution for different applications, for different challenges. I will just give you a short overview about these different solutions. We have solutions from Cadence in the area of PCB layout, and of course simulation with PSpice, simulation of signal integrity and power integrity. We call it a so-called power-aware signal integrity and power integrity solution. That means we also take care about the power planes in the inner layers of your PCB. A lot of other tools just ignore them and think they have ideal situations, but in today's designs with higher and higher frequencies, that's no more the case. Another solution we have in the area of timing analysis of digital circuits. The thermal behavior of PCBs can also be analyzed with a thermal solution, including external conditions, heatings, housing, and so on. And you can develop your complete cooling concept in this solution. For complex 3D applications, we have tools for integrating mechanical data as well as PCB data from the ECAD, and we can also analyze creepage and clearance distances. The solution we're going to look at today is about the reliability of your electronic circuits. We will see more details in a few seconds. Another solution is about chem verification, where we can analyze the chem data before you go into production, into fabrication. After fabrications, you need to test your PCB. This can be done with boundary scan technology. That's more and more very important because again the density of your circuits is growing fast, and with packages like BGA it's no more guaranteed that you have physical access to all the nets or pins. So that's a reason for looking into boundary scan technology. The last one is the protocol analysis, where we can analyze standard protocols for memories, DDR2, 3 or USB Ethernet interfaces. Over all these different solutions, you create a lot of data, for example the libraries, but also design data, and with several solutions we can manage these different data, we can version these different data, and we can also integrate into existing PLM or ERP systems. So most of these solutions are available not only for Cadence tools, which could be read out from the picture on the right side. So all these solutions I have talked about can also connect to any other PCB design tool. The same for the solution we will look at today. The same is valid for the reliability. So most of these solutions can be bought as perpetual licenses, but for a lot of them we also offer rental licenses which can be rent for 1 month or a year, so we can optimize the costs depending on your needs. We not only do the sales, we have a big support department with a lot of engineers, specialists who can assist you during your daily work. Of course, we also offer trainings and services. Okay, so with this, I hand over to Mr. Itzhak Pot from BQR.
Thank you very much for inviting me to present our FixStress to your customers. And my name is Isaac Bot. I am the founder and the CTO of BQR Reliability Engineering from Israel. We have developed the FixStress. It's a suite of several software modules. Mostly, the idea of the FixStress is to provide automatic electrical stress analysis and derating, which include also an automatic schematic review, which is based on the electrical parameters which we have calculated in the stress analysis. After that, when we have the actual stress level, we can calculate the reliability and the MTBF of the products. It's like a new concept of design for reliability, which encapsulated in the FixStress software package. So before I go over the tool, I will also want to present our company a little bit. We found the company in '89 as a consulting company in the field of reliability and maintenance engineering, more for the defense industry, and by the years we moved to the commercial industry also. And our team gained enough knowledge by performing this consulting project, and it's about 3,000 projects until today. And from that knowledge, we built up our own software, the FixStress, the CARE, and the APM Optimizer, which became the majority of our company to sell the products. And the team which provide the consultancy provide the support for the customers who buy the software. We employ a team of electronic and reliability engineers, different degrees, and they do the development, the algorithm, the software development, and the technical support. It's a short list of our customers. We have about 200 customers already, and the customers are in various industries, mostly electronics. Every system that have electronic need our software. And then you can see that in telecom, aerospace, automotive, railways, and so on. It's mean everywhere there is electronic box or electronic card, they need our software in order to improve the availability of the electronics. So always I ask customers design perfect. Almost they say no, and they found a lot of problems in the field or either in testing, and our idea is to detect all those hidden design errors which contribute to high failure, detect them during design, which the cost is cheap to do. So as a scale to understand what is the range of the cost of detecting an error and correcting it during the design, it costs $1 very cheap. You make the change in your design, your schematic, very quickly. But if you do that after the user detect the problem and the failure, then you need to go back, and this can cost you $10,000. And this is the range of between to detect it in the design and to detect it either by the user or after a test that you do, that you need also to go back and to redo the design. I that you remember the problem with the Galaxy Note 7, it cost them much more than $10,000, this problem. One of our customers gave us this chart which represents the return on investment. So you can see in this axis 51 boards. In this scale, you see US dollars. And every number here represents a PCB, a design. So in PCB number 9, they save about 1.5 million. In design number 13, they save 3 millions and so on. So the user accumulated the cost saving and come up that he saved in total for the 51 boards $3.5 million, while invested only 350. 51 boards, there are many engineers that are doing it. It was in a period of much less than 1 year. So you can see that the return on investment here was about 1 to 10, 350,000 to 3.5 millions. Here I show you the complete set of tools that we have, but later on we will concentrate only on the FixStress. So we are providing a scalable solution, end-to-end solution, starting from a component level and a PCB level, going up to a system level, which may be a box containing several assemblies, up to an asset which can have a few cars, a few trains, a few ships, aircrafts, or a distributed telecom system, or a distributed factory which have many locations. The FixStress start with, it's only for electronics. It has several modules, and it has an automatic schematic review. It has 2 phases, I will show you later on. Stress analysis, thermal analysis, and stress derating analysis. And it's also including multi-boards integration, when you can make this kind of analysis on not only on one board, but many boards together, connected by the connectors and the cables. Finally, you can do an MTBF prediction in various methods. So the next step is to take this reliability information of the assemblies to go one step further and to do a system level analysis. In this case, we also using mechanical components, and you can see that we can check the redundancy, how much redundancy you need in the system. It's a simple way to describe it is, for example, the power supply. If you have one power supply, if it fails, the system fails. So sometimes you put 2 power supplies in order to support the system, and when you have a fail in one of the power supplies, the second continue working, so you don't have a system failure. But you need to have a maintenance action to replace this faulty power supply, but the system continue working. So this is mainly used for critical mission systems, but also for other systems when you want to have long life. So in the care package, what we are doing, we are looking into the failures of the various assemblies, and we look if we need redundancies. We are detecting safety problems. We check the probability and the effect of any failure mode on the behavior of the system. We are checking the capabilities of the built-in test to detect and isolate failures, the time needed to remove and replace assemblies. And for the mechanical components, we have a simple module, the MRS, Mechanical Reliability Simulation, which is similar to the FixStress, but not such developed as the FixStress, is a low-level application, but it still provides us the reliability parameters for rotating mechanical components. When we go level up to the asset level, we want also to involve the maintenance actions. Until now, we talked about failures. In here, we're talking how we repair the failures and what is the maintenance concept. So first of all, we are calculating the life cycle cost, how much will cost the entire maintenance concept, including the spare parts, the time that you lose, the unavailability of the system. And based on that, we are starting to do some optimization process. The first one is level of repair analysis. This means if you need to repair or discard the assembly, what is better for your asset. Instructions for preventive maintenance, when to do that, how to do that, number of spare parts, the resources needed to support the maintenance, and some additional modules that are supporting various industries like RCM is the machinery industry and MSG3 is the aerospace. And finally, we have a module FTA, field data analysis, that if you are collecting your own failures of your assemblies, you can model those failures and build up the model, and this data goes back into the system as a field data instead of prediction data that is coming from here. Everything is supported by a core database, so you can put all the components, assemblies, failure modes, and everything is in the database, and you can reuse it between projects. Now, this chart represents the FixStress flow. So normally from the schematic design, you need 4 types of files: the BOM, the bill of materials, the netlist, the pin file, and the ICD. With ORCAD, we did an integration, and I will show you in a minute how it works. So all those files are generated automatically from the ORCAD. From the other tools, they are just interface, and they get the file and we import. But in ORCAD, we did the real integration. So this data goes into a process. The first process is automatic schematic review. We call it phase 1. Phase 1 is a step that the tool detects design errors, which are shortcuts, not connected, or design errors that will affect the stress. I will show you afterward some design errors which looks the error, you cannot detect it, but it will affect your design and will increase the voltage, the current, and you will need to increase the rating of the components, and this is by mistake. So why to do a stress analysis if you have a design error which will cause a high failure? So in this case, we developed this module that will detect design errors which will affect high stress. In the same time, this tool or this module can check the connection between 2 main chips. Before you go into details and design, you want to check to build up, for example, the connection between a large ASIC and a DDR4. There may be about 100 or tens of ways how to connect this ASIC to the DDR4. So we have already rules how you can check if your ASIC is connected correctly before you go into the detailed design, because again, if you have here a mistake, this will affect the stress simulation. You will get the wrong data and you will be misleading because there is a design error and you don't know. So the idea of this ASR, automatic schematic review, is to screen out all design errors between large chips and the design that affect stress. So after we did it up, we go to the stress analysis. And there are again here 2 steps. The first step is rapid. And this is a stress calculation which is done only on DC. And this can be done also on a non-completed design. This means that it can be done on 1 page or part of a page. You don't need to have the complete design. The precise is you need the full design. Everything should be there in the design. You cannot misplace a component or misuse a component and to have a few lines or nets are open, because in this case we are using loops. If the loop is open, we don't have a stress. In the rapid, we are using a different technology, which is a potential on the net, and we propagate it through the connected components. So in the precise. In addition to the DC calculation, we can do AC and also bus calculation. This means that we are toggling all the signals on the bus to detect the most critical combination which create the high current, and from the current we drive the voltage and the power. So those two modules generating the actual power, volt and current in two steps, only the DC and the DC plus AC. But in this stage, when we are in the schematic design, before we go into the layout, we need to also to know what is the temperature, and we don't have the layout. So we have developed a mini thermal analysis tool which take the power, and since we know the components thermal model, it's mean the package, the number of pins, the theta JA, theta JC, the heatsink if there is, and we build up the thermal model, we build up the equation, we solved them, and then we get only one number, which is the delta T, which this means the average temperature rise of the whole PCB from the cold plate and from the environment. It doesn't take into account the effect of one component on another, and doesn't take any other effects. It can take the effect of airflow when you blow up airflow, and it can tell you how much airflow you need to cool it down, or if a specific component you need to have a heatsink. So finally, we have the power, volt and current, we have the delta T, it means the temperature of the board, and then we can do a stress derating analysis. We detect overstress component, over design component, and then we need to go back to the design and to correct it. And if it's finalized and everything okay, we can do the MTBF, now based on part stress. And this is actual MTBF, written then as a parts count, which we don't need any stress, which gives you a high number. It's with a very low MTBF number comparing to the MTBF coming after the part stress. Now, after you build up, you make the layout, you have the production, and you have a prototype, you can make an external 3D thermal simulation, and then you can replace this delta T with this external, either from an infrared camera or from a thermal simulation, and then you can make a second run of the stress derating to see if this is still okay. From our customers, they are reporting that this delta T, it's not accurate. We call it quick and dirty. It's very quick, but not so much dirty, because the difference is only plus minus up to 3 degrees. So if you have a high temperature system like 60, 70, 90 degrees, 3 degrees will not make any effect. It will make a small effect, but you are in the range. This helps you to make an accurate stress derating before doing the layout, which is important. And this is also will give you guidance of the components with the high junction temperature, and then you can place them in a cooler area. So your placement will be more smart by knowing the thermal effect of the components before making the layout. Then this MTBF goes and feed the care system level and asset level optimization. Now, this is done for one board, this process. After you complete all the boards, you want to make a check, a system level integration. It means all the assemblies together through the connectors and the cables, because sometimes the definition of the signals from one board to another, it's written in a Word document or in an Excel or even in the pin type of the schematic, but you don't check it with the other card or the PCB with the signal from the other side, if the signals are okay, if they can get each other. I will show you an examples how it's done. So customers are reporting that here they are detecting additional additional design errors because of unclear or undefined signals between the PCBs. Everything is supported by the libraries. So here I will stop the presentation and I go to the ORCAD. Let's see. Okay. I believe that you see my screen now. So this is ORCAD. We have a very simple example here, which is a analog to digital converter. It's this chip takes those analog signals, convert them to digital, and through those drivers, push them to this connector. So in the ORCAD, in the integration, you can see that there is a FixStress icon here. Once I click it, I get this window. This window is not from our software, it's from ORCAD. It's embedded in the ORCAD. And this includes several icons here. Okay, so several tabs, sorry. Let's make it a little bit bigger. Okay, so first step is to define your parameters. So we need the reference designator, it's a must. Without that you cannot do anything. You need to have the manufacturer part number, the catalog number, it's mean your internal company part number, the manufacturer name, and description. By the way, the minimum, what we need is only the part number and the reference designator. The others, it's good that you have them, because if you have also your catalog number, there may be replacements, other part numbers, manufacturer part numbers, which are pointing to the same catalog number, and they are the two keys. So you can select components by either catalog number or the manufacturer part number. The manufacturer names, you need to know if you want to check the data sheet to know from where it's coming. And the description, if you have a good description, the tool is capable to pass the information from the description and create automatically the libraries, which is very important in this case because the reliability libraries, you may not have them, and if you buy the tool and you want to use them, to use it, you will need the library. So if you have a good description, the tool will pass it and create the libraries. So what you see here, just when you click on here, the part number, you get a list of all the fields available that were defined in this design below. And you select the correct field and you can see that it's okay. Now if you scroll down to the chip, any chip, you can see on the right side, this is the pin file. If you remember, we need to, in order to run the FixStress, in addition to the BOM, we need also to get the pin file. So the pin file shows you for every pin number, the name and the type. This is important to us, and if you don't have this information in your design, it's a pity. Then you will need to put it manually in the FixStress. But I believe that most of the engineers they are describing this type of signal. So I now click on the other tab, the BOM and the netlist. I will see here again the BOM. Now I can sort it also by part number, by catalog number, and so on. But see now the netlist of this design. We have 565 nets. It's very important for us. So we have seen until now the BOM, the netlist, and the pin file. We have here also the library. This means that every part number which is in this specific design, we can see the full set of parameters available in this design for every component. Some here is not so much, but other companies, they put a lot of parameters. Sometimes they are not used, so you can just look to see what are the parameters when you are in the setup to understand which parameter you need to put in. Then you have the results. And the results here are already done. So you get the reference designator, you get the part number, you get the failure rate of the component. You can sort it. You can see that this component provides the highest failure rate. Failure rate, this means number of failures per million hours. As this number is higher, this means lower. In order to know the MTBF, we take million divided by this number. In total, you can see on the bottom, we use this prediction method. In the environment is aircraft, subsea aircraft, 35 degrees. And you can see the failure rate is 8.2. If we take a million divided by 8.2, we will get 121 something. And what we can see here in the red one, the components which are overstressed. So in this case, here we can see the full list of components with all the stress data, the power, the voltage, and other parameters, including the junction temperature. And I can click here to show critical components only. In this case, I will see only the critical components. Now I want to see what's the problem. So I just select the first one. Let's take which one? This one, the first one. So if I double click on it, I get back to the schematic, and I see this schematic highlighted with the correct component there. So let's go back to the presentation. So I showed you now the process of running this integration. Now let's go on with the presentation. The idea of the automatic schematic review, which all the phases, the two phases, and the chip interconnectivity, is to extend the DRC with additional type of errors that is the tool is capable to detect. So we call it as a logical and a parametric schematic verification. We check the parametric values from the stress analysis and provide us additional layer of the design check. The rapid is using Ohm law, which is propagating the net potential, and the precise is using the Kirchhoff and Fourier analysis in order to implement the AC analysis. And in this case, you get over stress and over design components. Sometimes you can select a very small, very large or high rating component, and you can reduce the size of that component to a low one because the stress is very low. And then you can adjust your rating, and so select smaller components to save room on the boards and also weight. The ARS provide you schematic errors between boards. If we are looking into the chip interconnection, so we have a customer Mobileye, it's an Israeli company, which they do ADS system, automated driving assistance system, and they develop this chip which guide you on when you drive the car, if you close to another car, if you cross a lane, and some additional interaction with the driver. So this is the chip. At a very large chip, it says 2,500 chips. They need to be connected to a DDR. There are 22 ways how to connect, and we develop the rules. The rules are hierarchic. One, if you are using this technique, you need to check this, and so on. And in the past, they did manually checks, which take them more than a month. and now they do it in about 10 seconds to check if everything is okay. And they use it for all the car manufacturer which they sell this chip. If we're talking about the multi-board integration, you can see that every board can be designed separately, but if you want to know exactly if the rating and the stress are okay, you need to connect um, the boards together. For example, you have a power supply and you need to see what is the load or what is the current needed from the other board. And if you are in the schematic phase, you see the schematics, you see the signals, and you need to able to check the signals between the different boards. So finally, it gives you the check between the connectors. If one PCB is the pin is going to the right connector or the right pin or socket. On the other side, it gives you the size of the cables between the connectors. It gives you, if you have a power supply, the split between the pins, if the current is correct between the pins, and gives you also indication if the signals are okay. One board definition this was, and the other one it was this one by a shift of a few volts. So it's a sinus, but it's as a shift. So they, if you integrate them together, you have a problem because this one was not designed to have this higher voltage. So there is a problem. So once we connect the boards, we can check if this is okay, and then we need to correct something which will be the same level, or something like that. In one case, it will be a few volts, and then it can be the same TTL but at 12 volts, which will harm the circuit. So you need to synchronize all the signals between the assemblies. The idea is here that you have your design tool and you have your GUI, and you provide the files. Going into FixStress, you do the analysis and you get back the results as I showed you. So finally, after you complete your FixStress analysis, you can see that the MTBF of your system, in this case, it always twice. So this is temperature, and this is MTBF, and here you can see the MTBF of this board is 250,000, and after FixStress it came up to almost twice. So why we need FixStress as automatic schematic review? Mainly because it also calculating parametric values like stress and use the voltage, the current, in addition to simple design error check, and then this will much more your capability to detect design errors. Okay, so here's an example. You have here a simple design, which you have here the net name and the same net they are using on both sides of the resistor. In some cases it's okay. I saw that user they want to use this way, some not, but this caused this customer a big issue because he was seeing 28 volts across 10K resistor. So this means this resistor will produce a 78 milliwatt, and they have selected 63 milliwatts. So this is much more, about 15 milliwatts more. Then they need to increase the size of the resistor instead of 63 to 160. But there is not such resistor, so they move to 250 milliwatts. So this resistor will solve the problem of the 20 volt here. But this, it's only half part of the problem, because this 28 is driving this input and this chip, and this burn this chip. So, but the design error was that they just give the same name. They need to change the name. It was a different net name. So in this case, you can see we have about 14 groups of common rules. In rule number 7, detect it. In this case, it's a general rule. All the rules are general. Every one includes between 10 to 20 different variants of the rule, different type of cases. And so together it come up to about 200 rules, general rules, which we call it good engineering practice, that will affect stress. So this chart we took from one of the magazines showing what are the field failures. So you can see that the two main contributors to failures in the field are no trouble found, this one, and electrical overstress. The other, like fabrication, assembly, test, and so on, they are much less. So the FixStress target is to address those two contributors. And the first one, the no failure found, I will give you an example like this. So let's take a simple bus. This chip, the output goes to those inputs. Each one need, in order to operate correctly, 5 milliamps. This can generate only 12. So if only 2 are open, it's still okay. 3 or 4, we get a problem. And the problem that this cannot supply 20 milliamps. So what happened? The voltage is collapsing. While it's collapsing, it stacks. And somehow it's, if a technician comes to the board in the field, you see it stacks, it's not working, so he's replacing the card with a new one. And when he puts the new one, it's okay. He sent back the faulty one to the lab, and they check it, and they don't see any failure. Everything is okay. So it looks like a software error. Always people, they don't see a burnt component. They say, okay, this is a software problem. And they're looking to see what was the bug in the software that caused this problem, but they will never find it because there is no software error. It's a hardware error here, which is very hard to detect. Our software is capable to look into all the loops of all the buses and all the components to see if the current provided can be, it's enough to the ICs that needed current. The other side for the stress analysis, the contributors are that the engineer put a higher operating value than required. So if you look into the data sheet, the nominal in this case is power, let's say 100% 1 watt. You are not allowed to generate on this component in the red area. And from this temperature, it is derated to 155. Now, we say in order to have a safe design, a robust design, you are not allowed to generate the 100%. So we use a safety factor. In average, it's 50%. Some components it's higher, some components it's lower, depend on the type. And you are allowed to generate, to overload this component to be only in the green area, which is the recommended area. This is the over derating area, and this is over rating. So the idea of the software is to define for every component in which region it is, in the green, yellow, and the red. And if it's the yellow and the red, it gives you recommendations what you should change in the component, what is the rating that you should change in order to bring it back to the green area or to reduce the temperature, for example, by heating or cooling. In this chart, we can see this temperature. And this is a failure rate or a chance to a failure. Here all the components are on 10% stress. We're increasing the stress above all the components, and then we see that the risk of the failure going up and up. When we are down from 50%, it's still okay. Let's say, um, uh, and if we come up from 60 to 100, we can see that in 100, it even doesn't wait for us, it will bend almost immediately. It's like if you go by a lift, which allow to carry only 1 ton, and the manufacturer is using a cable that can carry 1 ton. So it will be a risk if it will take many times 1 ton. So the probability of that the cable will tear off will be very fast. But in order to have a fast, robust design, take a cable that can carry 4 ton. So you have a safety factor of 4 in this case. And this depends on the company how much room they want to keep for for safety or risk for a failure. It depends also on the type of the product, but mostly it should be below the 50%. Our stress analysis is capable to calculate all type of parameters for every type of component. If someone needs an additional parameter, all the data is in the database, so we can extract out the additional parameter. We are complying to European Space Agency, Derating, and other organizations which have Derating standards. Okay, now I will show you the schematic review phase 1. I will do it quickly because I don't have much time. So we have those general rules that everyone is based on from 10 to 20 sub-rules. Some of the examples. So this is the error which was detected by our software by one of our customers, and it was not detected with those tools. It tested with those tools, and they didn't found it. Once they run it with our tool, they detect it. Maybe you can say it's a simple one, and we will detect it. But anyway, this customer, they didn't detect it. It's a fact, and we could detect it for them. Another design error is this ground is connected, but it's floating. It should be connected to the ground. So a simple DSC will check if the ground is connected to any pin and say, okay, it's connected. But we are checking what is the potential. And we need, in this case, we need to see that the potential of this ground should be ground or very close to ground, depend on the connection here. And because we are doing it in the parametric way, we can detect this error, and the DRC cannot detect it. This is another error which you have here a circuit. You have here a pull-up resistor, which is not in the range with the manufacturer recommend from 5 to 10K, but the engineer put 3.3K as a pull-up, or in this case that he just forgot to put the pull-up resistor, and the tool recommend him to put the pull-up resistor. So in the rapid, as I said, we do that as a 1 second. I need to have coughing. Okay, I'm back. Doing the dissection, by propagating the potential through the nets using the simple Ohm law, but this is automatically done on all the circuits. And the idea here is that we are using all those sources for the data, for the potential. We pass the ICD, we pass the net list, the net names, we take the parameters from the libraries of the components, from the regulators, and so on. So we know the voltage from the behavior of the components and from the user input like a net name or a signal name or signal type. And then we are putting all using this information, and you can see that every name with the components get the value, and finally for every reference designator you get the voltage. This is a calculation here, and you can see that immediately you get a coverage of 81% of the voltage, the current, and the power. And you can, where it's not data there, you can enter manually what is the potential on the net, and then in this case, and then the tool will propagate this value to the making the stress analysis. From that information, and then you can see that this here was overstressed. It is 12 above 1K. After they found that it's overstressed, they found that the mistake was not with the rating, but with the range of the resistor. It should be 100 ohm instead of 1K. Then the power dissipation is much less, and they don't need to replace it to a higher rating. This is another issue. You can see here the voltage, 3.3 volt, goes to a power rail of a big chip. And you see the capacitors, the filter capacitors to every input. And this, they just forgot to connect this one. And so those inputs, they didn't get any voltage. So in terms of connections, all the pins, those pins of the chip are connected to capacitor to each other. It's connected, but doesn't get any voltage, and our tool detected because we are doing it in a parametric way. We need to, we check that if those inputs really get this 3.3 volts. In this case, they did not. If we go to the precise, we are doing in this case also the AC in the bus simulation. It's mean we are toggling all the bus signals on and off, and now we are doing a very complex analysis. We're building loops, Kirchhoff law, and can be millions of loops, and we have a special technology that can minimize the number of loops and simplify the model and calculating the current for every loop. And from the current, with the Fourier analysis, we can calculate the voltage and the power. It's a completely different way how to make the stress calculation from SPICE. It's different. But we also take into account for semiconductors, if you have here transistor, the two modes, saturation and cutoff. In the saturation mode, we're calculating the current, power, and the junction temperature, and the cutoff, we're calculating the VCE. Those parameters are going into our table in order to do the stress analysis and derating. As you see here, this represents the entire model or entire concept of how the FixStress is used. So every component gets some attributes from the datasheet. A chip have much more parameters. They goes by pin. Simple components goes by one line because you don't specify it for every pin. It's a general parameter for the entire component. So this data is going into is translated into the small and H parameter models, creating those Kirchhoff models. And they are connected through the netlist. So the pins of all the components are connected through the netlist. Then we are generating loops. We have roles and test vectors. The test vectors is like the transistor is on and off. Running this complex equation matrix, and we solve them, and we are finally get the current. From the current, we get the voltage and the power. You must specify or tell the tool what are the signals that go in, because if you don't specify the signals, it's like you put the PCB on your table and you try that it will work. It will never work if you don't connect it to a power supply. The same as in our software. You must provide the information of all the signals on the connectors. This is how the signals are described. You have the connector pin type. If it's a DC voltage, if it's a rectangular, you specify the parameters. Everything is also shown as a graph in graphic, but as a summarize, you get it in a table because this is easier to document. You get the current budget for every power supply, how much need from external power supply to feed in, what is the current above or on any pin on the connector. If it's enough, you need to have several pins or a thicker pin to carry this current. We can provide or implement DC to DC converter on the board. These are the type of DC to DC that we can handle, and this is the model. By the way, our tool is not so good for switching power supply, and the main reason is that you need also to know the magnetic model for the transformer. This is very complex to get, and more trial and error with this transformer. So in this case, I recommend the customer, if they have switching power supply, to really use the PSpice, and then it can provide information. But our board is capable to run on a very large board. The largest one which we did was 25,000 components with 100,000 pads, and this took about 5 minutes to run, to provide all the information accurately, and this board was many CPUs and DSPs and DDRs and ASICs, which are very complex to model with a SPICE. So our tool, let's say, for doing real stress analysis is better. And another thing also, that the SPICE provide you the signal wave, how it looks like. We are not providing the signal wave, and because we are looking on what is the maximum stress on that component, and it's a different way and a different purpose how you look on stress. We have also the user need to specify the frequency of the clocks. It can be interrupted also from the net name. If you have the frequency, the net name, so the tool can pass it. And this is a few examples. For example, this is an RF module. We generate here 2.4 gigahertz, and the engineer connect here capacitor of 10 microfarads on this line. So this is a big mistake, because this will short the frequency around and will harm this chip. Another problem is this transistor, which in the net name it's written 3.3, but it was not correct. It was 12 volt that is coming from that page. driving this gate, and the maximum was allowed is 8 volt. In this case, this is a DC to DC converter, which the user make a mistake by switching between those two resistors. Because of this switching, he got here 3.2 volts. The tool detected this here 3.2 volt instead of 1.6 and reported an error. In this case, you have here Zener, which provide you 10 volt, 12 volts. It goes through this line from this page to this input, all the way here to this gate. The maximum here was again 8 volt. So this resistor, if they didn't correct it, it will blow up later. So now we're coming from the last phase, the schematic review, which is the last step before you finalize. So in this case, we have rules that the user can define in a simple editor. In this case, which we take for example, a good engineering says that on a parallel to a crystal, you need to connect a capacitor. So our tool have a very simple definition. You have the first object, second object, and what is connected between. So in this case, the crystal, it's a net which carry a crystal, or can be from the component library. Note that this RefDes is a crystal and to the ground, and it should be connected the capacitor with this rail, and it should be connected. If it's not connected, this is a major error. And for example, another one which has a NC, if you define the P name as NC, it should be not connected. You cannot connect a signal to a pin of a chip, which is the name is an NC. And the others you can define, for example, the pull-up resistor, pull-down resistor. And every rule that you can define between two objects, and the objects can be a net, pin type, pin name from both sides, and what it can be connected. This is an error which can be detected in this way. You have here a 5 volt as a connection to the chip, and this chip can get only 3.6 volt. So this is again a design error. And now I will show you a little bit about the thermal, and that will be my presentation. So let's take a simple board which have the power dissipation at about 12 watt, and the average temperature rise is 35 degrees. So this is because this is not a high watt, but it was a very small PCB. And then it generates 14 overstress components. And if we put airflow of 800 CFM, you see that the delta T went down from 35 to 10 degrees only, and 6 critical components. Now we took another example, which another assembly with few PCBs here. So that the power dissipation in this case was 24, the delta T was 6.4. So you can see this is the result from our tool. So it was done in 71 degrees plus 6.4. It gives us 77.4. So this is the entry point for the components. Now, for every chip, for every component, since we know the exact power supply, the power dissipation, so we could calculate exactly the junction temperature. So we come up with a table for every chip, the junction temperature in a Pareto from the upper level to the lower level. Later on, when they build it up, they build and they make the 3D simulation, they checked with our result, it was almost the same. But in this case, if they did it, they know exactly which component is hotter, and they can put it in a cooler area. And finally, the prediction, we do all the kinds of predictions, the FIDES, the Milenburg 217, the Telcordia, the Cine, and the Siemens. And of course, this drive our reliability analysis tools. So as a conclusion, so FixStress is a design for reliability tool. It's integrated with popular EDA tools. It's used through the design process. It'll give you high ROI, return on investment, and your final product will be much more robust. Our customers are reporting to us that in average, after let's say 5 years of using the software, that the time of the developing and time to market was reduced by about 50% due to design errors in the field or by the customers, and even the integration tests are reduced because they don't find any problem there. So this concludes my presentation, and I want to thank you very much for listening to me.
For any questions, please feel free to contact us by email or phone, and we will make sure that we can answer your question. Thanks again for your attention. Thank you. Bye-bye.